All right, so this is organic chemistry and just the basics. Today, I'm going to be going over my opinion of organic chemistry as well as majority going to be structures. What is OChem? So OChem is pretty similar to inorganic chemistry, yet it's more so carbon-based chemical reactions. Organic chemistry provides an understanding of carbon-based mechanisms, which will lead into biochem and a majority of every other reaction in the world. OChem is what you learned based off of inorganic chemistry. However, in my opinion, I think OChem is more fun, right? OChem is mostly 90% reaction based. Therefore, learning how to draw these mechanisms and learning how to draw the reactions step by step is pretty fundamental. I would say that how do I say this? Organic chemistry is similar to physics and calculus in a way that it's not just brute force memorization. However, there aren't many calculations when it comes to OChem. It's more so figuring out what goes with what is synthesized, what reaction causes this compound to become another compound. Synthesis is a very crucial aspect of OChem. All right, on to the main part of this video, which is structures, right? As you learn in inorganic chemistry, every single compound has a different molecular geometry. Some of the ones that are mostly found in organic chemistry would be carbon, which is normally tetrahedral. Let's see. Uh, there's also linear, bent, and trigonal planar. Carbon, which is normally bonded to 4 different compounds, is known as a tetravalent. Nitrogen, which is trivalent, and oxygen, which is divalent. For halogens and hydrogen, they're monovalent, so they're only bonded to one thing at a time. Brushing up on valence electrons. Since nitrogen is trivalent, which is bonded to 3 different atoms, it has one lone pair to make up this full octet that you see. Seeing that each bond to the hydrogen is sharing 2 electrons, 2, 4, 6, 8, which is a full octet. As you can see over here with the water, there's 2 lone pairs and there's 2 hydrogens making up that octet. Hybridization. Hybridization is the molecular geometry. However, it comes into play with different types of reactions. As you can see with this sp3 hybridized carbon, the black triangle is going towards you while the black lines are going away from you. This is represented as with the black triangle and the black lines. As you can see in this comical right here as well, this clearly is going towards you, while this is going further away from you. Constitutional isomers. Constitutional isomers are compounds that have the same formula, non-superimposable, and they have different characteristics and properties in real life. Diethyl ether, the one above right here, has an oxygen in the middle and 2 methyls coming out the side. Ethanol, which is 2 carbon chain connected to an alcohol group, which is OH, is completely different in physical properties. Dimethyl ether. Dimethyl ether is normally not, this is actually diethyl ether. It has a completely different property compared to ethanol. Ethanol is usually used in hand sanitizer and gasoline. In enantiomers. So they have the same chemical formula, but different stereochemistry, and they are superimposable images. So this is a picture of an R2-bromobutane. Butane has 1, 2, 3, 4 carbons, 1, 2, 3, 4 carbons, right? This one has a bromine coming towards us, while this has a bromine coming away from us. Although it looks similar, it has entirely different chemical composition, same chemical formula, different compound. Chirality. So when a carbon is connected to four things, it has it's characterized by either S or R. R being going clockwise, while S is going counterclockwise. And this is based on the atomic number of each compound connected to that carbon. As you can see here, this carbon is connected to an O-methyl group, an alcohol, hydrogen, and a methyl. Priority goes to this O-methyl right here due to this oxygen then being bonded to this carbon, while this oxygen only is bonded to a hydrogen. Because of the secondary compound having a high atomic number, carbon is higher than hydrogen. Therefore, this is the most priority, then the alcohol, and then the methyl, due to the fact that alcohol, oxygen, has a higher atomic number than methyl. So just looking at this, you see O-methyl, alcohol, then methyl. And as you're counting in that direction, it is a clockwise pattern. If you look at the second one, it's the opposite, which results in an S pattern, counterclockwise. Diastereomers are a sub-branch similar to enantiomers, yet they are not mirror images of each other. As you can see from this top picture right here, let's see, 1 and 2 are enantiomers, but the rest are diastereomers. So if you took this and you put a line right through the middle, you can see that you can actually flip it. However, for the rest of the compounds, they would not be able to be flipped or mirror image. Chair conformations. Chair conformations are cyclohexanes drawn in a way that you can see their properties and the way that it's bonded to the cyclohexane. So the reds are clearly going up while the blues are going to the left and the right. Normally, the ones going up and down are considered axial, which has a higher energy, less stable, and therefore any compounds connected to the cyclohexane would prefer to be equatorial, or most of the compounds. There are situations where there are multiple compounds connected to the cyclohexane, and that results in both axial and equatorial positions. Types of arrows. This is very, very crucial in terms of organic chemistry. A couple of arrows referenced here is bonding arrows. So this potassium oxyhydride is bonding to the hydrogen off of this ethanol. As this oxygen comes closer and closer to this hydrogen, due to the fact that it wants to take the hydrogen away, we draw this arrow to signify that it's starting to pull off this hydrogen. During this transition state, this hydrogen will break its bond with the ethanol oxygen, resulting in 3 lone pairs, which are not drawn in here, but 3 lone pairs, which means that the oxygen will be negative. Well, this produces water. But the potassium ion is actually going to bond and make an ionic bond with this ethoxide here. So to re-clarify, bonding arrow right here, oxygen to hydrogen. Cleaving arrow is this transition state arrow right here, where it's cleaving off its bond. And resonance arrows are to represent the movement of pi bonds throughout a compound, which we'll reference next. And transfer arrows are when you draw an arrow to show that there's a hydrogen or methyl transfer within a compound that has a carbocation. Resonance arrows are drawn right here, as you can see in the red. Is the delocalization of charge throughout a molecule. Compounds resonate to push negative charge towards the elements that are most stable with a negative charge. So, for example, here, you can see that this oxygen has 3 lone pairs, and it can actually resonate down, making a double bond with this carbon right here. And since this carbon already has a double bond, this double bond is going to resonate towards this other double bond, which will resonate back up to this oxygen, producing this other interstate. Right?